Then for 95% confidence interval, we know the confidence region is minus 1.96 to plus 1.96. So on the positive side, we have 0.025 as the error region, going from plus 1.96 to infinity. And on the negative side, we have error region going from minus 1.96 to minus infinity. And that area is also 0.025. So together, these two areas contribute 0.05. Okay, so 95% for 95% confidence interval, the critical values of Z are minus 1.96 and plus 1.96 when it is a two-tail testing. You are allowed to make use of positive and negative side both. So when we are allowed to make use of only the negative side or only the positive side, that is greater than or less than test, the critical value naturally has to move more towards 0. So the critical values are 1.65 as opposed to 1.96 and minus 1.65 as opposed to minus 1.96, closer to 0. For 90% confidence interval, the critical values of Z are minus 1.65 to plus 1.65. Note the repetition of the numbers minus 1.65 and 1.65 from 95% confidence interval. So that is explainable easily. 0.10 is 0.05 plus 0.05. Okay, so you can naturally relate the two-sided 90% confidence interval with one-sided 95% confidence interval. And for this 90% confidence interval, the left side critical value of Z is minus 1.28. Right side critical value of Z is plus 1.28. 99% of course is very strict. So the critical values are minus 2.58 and plus 2.58. When we take only one-sided test, then minus 2.33 and plus 2.33. So you can see that everything is in the backdrop of standard normal curve. Okay. Now, this use of standard normal curve is permitted when the sample size increases 30. When it is not, then what to do? We have to make use of other distributions. So that discussion is pending for some time. So pictorially, the 95% confidence interval is from minus 1.96 to plus 1.96, as you see. 90% minus 1.28 to plus 1.28. 99% minus 2.58 to plus 2.58. And we know that when we are allowed only one-sided test, the critical region, the critical value of Z moves inward. So plus 1.65 to infinity is the 5% level of significance region. So these terms, 5% level of significance, 95% confidence interval, their significance we are going to explain through two concrete problems that we'll do. So minus 1.65 to minus infinity is the region of error or region of rejection. Now we illustrate these concepts with two examples. I believe one of them you have seen before, but we will go back to this. But all in the backdrop of standard normal curve. Now a concrete situation, a factory has a machine that the factory claims dispenses 80 milliliter of fluid in a bottle. This needs to be verified. A sample of 40 bottles is taken. The average amount of the fluid is 78 milliliter with standard deviation of 2.5. Verify the factory's claim. You recall that the verification of the claim has to be done in a principled manner. The emphasis is on principled manner. So I observe 78 milliliter is less than 80 milliliter. So naively, I can take a stand that since out for this 40 sample size, since the mean value is less than 80, I reject the hypothesis. But that will be naive and not principled, because probability theory gives us a method of taking a much more principled approach. So what are the variabilities here? The sample size can increase or decrease. Then there is this additional factor of standard deviation, which also has a bearing on the decision of rejecting or accepting the claim. So there are these parameters: the sample size, the standard deviation, and the target parameter, which is the mean. Okay, but sample size and standard deviation has a bearing on the decision through the central limit theorem. Now it is time, I think, we have to revise central limit theorem in one of the subsequent lectures, which we'll do. So this is the claim. Now just reflect a bit on the nature of the problem. Now there is some fluid being bottled, and what is the sensitivity with respect to the amount of fluid in the bottle? Now, if the fluid is, let's say, some Coke or Pepsi or Miranda, and if the amount falls below or above 80 milliliter, then it is not as serious a situation as when the fluid is required, let's say, for saline for a patient. Okay, a medical or health situation would be much more serious than a sort of entertainment situation. Okay, so the strictness of alpha, the level of significance, is much more in case of a health situation. If 80 milliliter is for some kind of medical fluid, then we cannot take liberty with the amount. The region around 80, the region of tolerance has to be very small. Okay, but for cold drink, we can be more permissive. So remember this point, because we have to discuss the significance of alpha, the level of significance. So 40 bottles sample has been taken, and we see 78 milliliter, standard deviation 2.5. Now I enumerate the steps involved in hypothesis testing. First and foremost is examining the problem carefully. Okay, so these are informal statements, maybe a bit philosophical also in nature, but things begin with this step. Examine the problem carefully, read the problem statement again and again, and discuss the situation or the issue absolutely threadbare. Then comes the most important step. Formulate H0, the null hypothesis. Okay, when you formulate H0, automatically the alternate hypothesis also gets formulated, which is the negation of null hypothesis. The alternate hypothesis is also called the research hypothesis, which we are trying to establish by rejecting H0, the null hypothesis. The next important step, which is independent of H0, mark it, it is independent of H0, is deciding the confidence interval, usually 90, 95, or 99%. And this depends on how permissive we are with respect to committing an error. Okay, how permissive we are with respect to error or tolerance. So this automatically fixes the significance level at 0.10, 0.05, or 0.01. So once we fix H0, the null hypothesis, and the level of significance, This sets the rule of the game, and those rules cannot change going forward. Okay? So let's remember these two steps we have taken, these two actions we have taken: formulating the null hypothesis and deciding the level of significance or the confidence interval. So we will again make reference to a logic-based situation, a non-probabilistic situation, which is quite markedly different from the methodology here. The next decision we have to make is our testing going to be two-sided or one-sided? So two-sided is typically used for equal to test, and one-sided is used for greater than and less than test. Normally, when we look at different problems of hypothesis testing, we typically relegate greater than or equal to decision into the alternate hypothesis. It is more convenient to work with null hypothesis, which is in the form of equal to. Okay, equality as an operator gives us many advantages with respect to mathematical formulation and working with that formulation. So after that, we have to decide what test we would perform. Z-test, which is in the backdrop of standard normal curve. T-test, when the sample size is smaller than 30 and without replacement. F-test is another situation. And chi-square test is when we have a sequence of observations and we want to fit a distribution to that sequence of observations. And you did see a number of examples for chi-square testing with respect to normal, binomial, uniform, and Poisson distribution. We would like to go back to them in light of what we have understood in hypothesis testing. So the most common test used is Z-test. And in case of Z-test, the critical value of Z is minus 1.65 for 90% confidence interval, plus minus 1.65, plus 1.28 for upper 90%, and minus 1.28 for lower 90%. For 95% confidence interval, it is minus and plus 1.96. 99% it is minus 2.58 and plus 2.58. There are corresponding values for upper and lower interval test. Okay, so to summarize, we have taken action on H0, null hypothesis, decided the confidence interval, and decided the kind of test, Z-test, T-test, etc. So let's move forward with Z-test. And we look at the problem that is under discussion now. After we have decided H0, we begin examining the consequence of H0. We have done the null hypothesis fixing. Under null hypothesis, what can we say about the data? Okay, and for Z-test, we'll get ZO, the observed Z, from the data. And if ZO is inside the reject region, we will reject the null hypothesis, reject H0. This is the methodology. Let's come to the problem under discussion. The claimed population mean is mu equal to 80. The factory claims its bottling mean, average bottling amount is 80 milliliter. And we have taken a sample of 40 bottles. The sample mean is 78. Standard deviation is 2.5. Now the null hypothesis we make is that indeed the population mean is 80. That means factory's claim is correct. The factory's claim is 80 milliliter per bottle. So this we would like to reject. Remember, we would like to reject this hypothesis. And there are three options for alternative hypothesis. Mu is not equal to 80, greater than 80 and less than 80. We'll work with mu is not equal to 80, and not equal to 80 serves our purpose. If it is more than 80, then it is an economic loss for the factory. If it is less than 80, then the customer is being cheated, which is also undesirable. So since we have assumed the mu is 80, population mean is 80. So under null hypothesis, we would like to examine what is the consequence. So since we have also decided the confidence interval to be 95%, the critical value of Z is minus and plus 1.96. Now under null hypothesis, what can we say about the Z observed? So Z value is population sample mean minus population mean divided by sigma by root n. So we can take any random variable, subtract mean from it, and divide it by the standard deviation. We'll get a standard normal variable. So since we have made the null hypothesis assumption, I can write the population mean to be 80. Okay, see the immediate consequence of null hypothesis. If I did not have that hypothesis, I would not know what the population mean mu is. Now, the sample mean is 78. Standard deviation is given as 2.5 and sample size is 40. So this gives me minus 2 divided by about 0.4, and that gives me minus 5 as the Z observed. And Z critical is minus 1.96 and plus 1.96. So minus 5 falls in the rejection region. So you see the rejection region is from minus 1.96 to minus infinity and plus 1.96 to plus infinity. Minus 5 is less than 1.96, so it falls in the rejection region. Okay, so since it falls in the rejection region, we can reject the null hypothesis. We can reject the claim of the factory that average amount of fluid in every bottle is 80 milliliter. This is not the case. Okay, now one may come back and say that why all these nitty-gritties, why all these actions, hypotheses, and so on. I had told you before by looking at 78 milliliter per bottle that you cannot believe the factory. I told you before. So why are you doing all this? No, we say that no, we have a scientific methodology to reject or accept a hypothesis. So we are resorting to that particular methodology. Okay, starting with null hypothesis and confidence interval and the nature of test. So this is what we have done. If we accept 95% confidence interval or 0.05 as the level of significance, we have to reject the hypothesis. Now, if we take 99% confidence interval, naturally, we will be more strict. Okay, and this region will now become more constrained, and minus 5 is still less than the Z critical value. Minus 5 is less than minus 2.58. So for 99% confidence interval also, the hypothesis is rejected. Okay. Now, what about 90% confidence interval? Because that is more permissive. But minus 5 remains still less than minus 1.28. So 90% confidence interval also, the hypothesis is rejected. So in this case, 90%, 95%, 99%, all these confidence intervals lead to rejection of the null hypothesis based on the evidence, which is the data. Now, what about the greater than test and less than test? We'll come to greater than and less than test in case of this factory filling the bottle situation. So greater than and less than test also are important, as I said. Greater than 80 will be economically lossful for the factory, and less than 80 um, uh, will be a loss for the customers. Now we take uh, the definition of hypothesis, which is inspired by sentiment analysis. So we have observations in the form of data. H is the hypothesis. P is the person holding the hypothesis. And T is the time when this hypothesis is held. So this tuple-based definition should be familiar to people working on sentiment analysis, where there are 5 tuples. The fifth component of the tuple is with respect to a feature of the entity. Now, in this case, the data, the hypothesis, the person holding the hypothesis, and the time of hypothesis, all of these are important because the hypothesis will differ from person to person, and it can also change with time. So we in our last discussion, we took this example of COVID situation. Okay, so we'll come back to this definition of hypothesis testing, which is important in terms of its components. Now we take another problem, mainly to understand again the confidence intervals and the strictness of the level of significance. We have this problem here. The mean height of 50 male students who showed above average participation in college athletics was 173.3 centimeter with a standard deviation of 6.4 centimeter. While 50 male students who showed no interest in such participation had a mean height of 171.5 centimeter with a standard deviation of 7.1 centimeter. We ask, is it the case that male students who participate in college athletics are taller than other male students? Okay. Again, and a very common situation, we can relate to this situation in our life, day-to-day life. And we would like to examine this question. Do the athletes have more mean height than those who do not do athletics or sports? Okay, so this is the question we are examining, and we have some data also at our disposal. Now, looking at 171.5 centimeter and 173.3 centimeter, can we claim that athletes are taller than non-athletes? Again, we are vexed by other controlling influences, namely the standard deviation, 6.4 centimeter for people who are participating in athletics and 7.1 centimeter for people who do not. So standard deviation is an influencing factor, and also the sample size. The sample size is 50. Okay, so if it was less or more, what could we have said? The sample size also has an influence on our decision. So now let's go through the standard procedure. So null hypothesis in the form of an equal to expression is always convenient. Okay, and very interestingly, you will see how the null hypothesis influences the mathematics going forward. So we assume mu1 equal to mu2, where mu1 is the population mean for people who participate in athletics, and mu2 is the population for people who do not participate in athletics. Okay, and we start with the null hypothesis that mu1 is equal to mu2. So this is my null hypothesis, and alternative hypothesis is mu1 is not equal to mu2. In particular, we are interested in the question, are athletes taller than the population which doesn't do athletics? Okay, So alternative hypothesis is mu1 greater than mu2. So now we have formed a null hypothesis, the most important step. Let's examine the consequence of this null hypothesis. So let theta1 and theta2 be the sample means. So we have taken a sample of 50 athletes and 50 non-athletes. And since we are assuming that there is no difference between the mean height of these two categories of people, then mu theta1 minus theta2 equal to 0. Okay, so this is a little more intricate. This expression is a little more intricate. So we take samples of size 50, okay, and we take many such samples. So each sample will have its own mean. So x1 bar, okay, x1 bar will vary from population to population of male athletes. And similarly, x2 bar, the population mean, will also vary from sample to sample for non-athlete males. So theta1 will vary from sample to sample. Theta2 will also vary from sample to sample. And theta1 and theta2 are sample means for athlete males and non-athlete males. So now I take the difference of theta1 and theta2, theta1 and theta2. That also is a random variable, right? I think you can see that. Theta1 and theta2, the difference is also a random variable. It will differ from sample to sample. Now, the mean of this difference is the mean of the population when we take the difference over the whole population. Okay, and that by our null hypothesis is 0. Okay, there is no difference in the mean height of athlete males and non-athlete males. So population mean in this case is 0. What about the population standard deviation? Random variable, remember, is the difference of sample means. What about the standard deviation? Now, standard deviation we know gets added up. So, or the variances get added up by central limit theorem. Now, 6.4 was the standard deviation for male athletes. So 6.4 square is the variance divided by sample size. That is the variance of the athlete population. Okay. And 7.1 square by 50 is the variance of the non-athlete population. So we have to add the variances and take their square root to get the standard deviation of the random variable we are interested in. Okay, reminding you that we are interested in the random variable theta1 minus theta2, which varies from sample to sample. So in our case, the theta1 is 173.3 and theta2 is 171.5. The sample mean for athletes and sample mean for non-athletes. And this is the mean of sample with respect to the difference of male athletes and non-athlete males. So athlete males and non-athlete males. So this difference is the difference of means, and we know that when two samples are considered, the mean of the difference is equal to difference of means. Okay, but variance is summation of variances. This came from central limit theorem, which we had done a few months back. Okay, so let's proceed, and when we'll go back to central limit theorem, all this again will fall in place. So for this random variable 173.3 minus 171.5, we subtract the population mean that we are doing to convert the random variable into a standard normal variable, and divide it by the standard deviation of the difference of means, and that is 1.35. Okay, so the Z observed comes out to be 1.33. Okay, Z observed comes out to be 1.33, all due to the null hypothesis. After we have formulated the null hypothesis, we are allowed to take all these steps. Okay, so that has led us to a situation that Z value is 1.33 when the sample mean is 173 for athlete males and 171 for non-athlete males. Okay, so this is done, and now let us see what we can say from the Z test. So we see that Z critical is 1.96 and minus 1.96 for 95% confidence interval. So we cannot reject the null hypothesis at 95% confidence interval. Why so? Because it is 1.33 and it is falling in the region minus 1.96 to plus 1.96. So this Z value is falling within the confidence interval 1.33 minus 1.96 to plus 1.96. Since it is not in the rejection region, we cannot reject the null hypothesis. Okay. What about 99% confidence interval? Z critical is 2. It should be 2.58, and again 1.33 is in the region minus 2.58 to plus 2.58. 1.33 is the value. So again, we cannot reject the null hypothesis. So the interesting case comes when we take 90% confidence interval. So for 90% confidence interval, the region is minus 1.28 to plus 1.28. So now we have entered the rejection region and we can reject H naught. So what does this mean? We can reject at 95% confidence interval and 99% confidence interval, but cannot at 90% confidence interval. What does this mean? So let's do this interpretation now. So this analysis now is linked with the type 1 error. Okay. Is linked with the type 1 error. The probability of type 1 error is 10% when the confidence interval is 90%. So type 1 error says reject the hypothesis when it should be accepted. So type 1 error arises when we reject the hypothesis when it should have been accepted. Okay. So let's examine this for our problem. So we go back to the definition of level of significance. Given a hypothesis, the maximum probability with which we would be willing to risk a type 1 error is called the level of significance. This definition is very important. We'll have to come back to it again and again. The maximum probability with which you would be willing to risk a type 1 error, this is called the level of significance. So in case of this athletics participation problem, what can we say with respect to the level of significance? Suppose alpha is 10%. Then in 10% cases, that is 1 in 10 or 10 in 100 or 100 in 1000 or 1000 in 10,000, as the number increases, we have more and more confidence. We'll make an error if we reject H naught when we should have accepted it. Okay, and recall what is H naught. There is no difference in the mean height of those who do athletics and those who do not. There is no difference in the mean height of those who do athletics and who do not. Okay, this is my null hypothesis. And if the level of significance is 10%, then if we reject this hypothesis, that is, we reject the hypothesis that there is no difference in mean height of those who do athletics and those who do not, then in 100 cases out of 1000, we will commit an error. Okay, and so if we are prepared to tolerate that kind of error, that will go wrong in 100 out of 10,000 cases, then this 90% confidence interval is fine, and we are all right rejecting the hypothesis, null hypothesis. Okay, so if we say that there is no difference in the mean height of those who do athletics and those who do not, that is the type 1 error we are committing. Now, if we are less strict, okay, if we are less strict, that is alpha is equal to 0.1, we are prepared to tolerate 10 errors in 100 cases. We will reject the stand that there is no difference in mean height. If we are more strict, that is alpha is 0.05, prepared to tolerate only 5 errors in 100, we will not reject the stand. Okay, and if you are very, very strict, prepared to tolerate only 1 error in 100, we will not reject the stand that there is no difference in the mean height. Okay, so this is the meaning of level of significance, and it has very close relationship with null hypothesis and the seriousness of rejecting and accepting depending on the nature of the problem. So as an exercise, as a thinking exercise, I will request you to consider the level of significance for the bottling question. The fluid is kept in the bottle, and also the situation of cancer positive, non-cancer positive, COVID positive, non-COVID positive, okay, and the situation of part-of-speech tagger from, let's say, Microsoft being better than part-of-speech tagger from IBM, okay. The sentiment expressed on a camera based on the lens versus sentiment expressed on a camera based on its weight. Which sentiment is more serious, sentiment on the lens or sentiment on the weight or color? Okay, so based on all these questions, we'll fix the null hypothesis, we'll fix the confidence interval, we'll adopt a test, Z test, T test, etc. Okay, so we have now given a more concrete step to hypothesis testing, and we are prepared to take up problems from many different fields, including NLP and machine learning, with much stronger foundation on hypothesis testing. Okay, we'll stop here and see if there are any questions and discussions.
Hi, sir. Morning.
Yeah.
Sapan here.
Yeah.
So the last example that we discussed, right? So if we map it to like when we are developing new algorithms. So let's say algorithm 1, I came up with. Algorithm 2 is state of the art. So I run algorithm 1 for 50 times. I have F1 score for 50 samples for algorithm 1. Similarly, algorithm 2. I do the same exercise, and if I reject S0 with 95% confidence interval, means I'm doing better than SOTA. Is this thinking right?
Sorry, you'll have to come again.
So let's say algorithm is something that I developed, and I ran that algorithm to calculate F1 score. 50 times I run the algorithm, so I have 50 F1 scores from my new algorithm. I do the same exercise with some state of the art. I have 50 F1 scores, and I do the same exercise that we did currently. And if I can reject H0 with 95% confidence interval, then it means that my algorithm is doing better.
What is the null hypothesis in your case?
The mean are same. So means the F1 score for both the algorithms are same.
Okay. F1 score is both the F1 score is same for both the algorithms. State of art as well as your own algorithm.
Yes.
Right. Achha. And now, so first step you have taken is you have formulated H0, that these two performances are same. These two algorithms have same performance. Achha.
Yes.
Okay. Then you decide on the confidence interval, which is 95%. Okay. Yes. So level of significance is 0.05. Achha. Now you perform some Z test, and let's say the Z observed falls into the rejection region. which is beyond 1.96, right? Okay. You will have to, of course, map the f-score to an
Yes,
appropriate
exactly.
standard normal variable.
Yes.
And now you reject, acha. So you reject, and since the level of significance is 5%, that means in 5 out of 100 cases, you are erroneous. You have made a mistake by rejecting the hypothesis.
Yes. So
In
95. Sorry. Yeah. So 95 times I am. So means are different for 95 times out of 100. Right.
Wait. So you are rejecting the hypothesis. That means you are saying that my algorithm is better than or worse than, let's say, better than the state of the art. Okay. Yeah. Yes. And if from the data you get a value of Z in the rejection region. Yeah.
I mean, something like this is what we need to do when we write papers. I mean, when we are developing some algorithms.
Yes.
And of course, that upper thing will come into picture. I mean, if we are better than state of class.
Yeah, the critical value will be 1.65.
Yeah, correct.
Yes, so you can have 95% confidence in your claim that you are doing better than the state of the art.
Yes.
Okay. If your F scores indeed take you into, keep you in
rejection region.
Take you into the rejection region. Yes, that's right. Yeah.
Yes. And so if it's 50, like I run my algorithms for 50 times, then I do Z test. If I do it for 20 times, probably I'll do T test or something like
that. Yes. Then you'll do T test. That's right. Yes.
Okay. Thanks.
Anything else? Any other question? Okay. So if not, then in about 5 minutes, we'll meet for work update for information extraction group. Kaveri has already sent the link.
Yes, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.